one more review video for you. So here we have a problem where you're asked to calculate the period of the oscillations of a thin ring when hung from a nail on the wall. The radius of the ring is 0.5 meters. The mass of the ring is 1 kilogram. So as you can see in the picture, we have the red thing is the ring. We have a nail on the wall. We hang the ring from the nail and we push the ring, say, to the right. We let it go. What is going to be the period of the oscillations, small angle oscillations of this thing? All right. So the kind of problem that we're dealing with here is called a physical pendulum. Clearly that thing is going to oscillate back and forth like a pendulum, but it is not a thin string with a bob at the end. This is a ring, as you can see, so it is not a simple pendulum. Any pendulum that is not a simple pendulum is called a physical pendulum. So in the video that we discussed physical pendulum, you were given this equation. This is also an equation that you can find in your formula sheet. So the angular frequency of the oscillations of a simple pendulum, of a physical pendulum, is the square root of mgl divided by moment of inertia with respect to the center of mass plus m times l squared. The denominator can also be written as the moment of inertia of the object with respect to the pivot. In this case, the ring, moment of inertia of the ring with respect to the point where the nail is. That's the pivot. So from the angular frequency, we can get the period because the relationship between the two is that the period is 2 pi divided by omega. So if we put then 2 pi and then we flip numerator and denominator in the square root of 4 omega, then we get the period. 2 pi, the square root of the moment of inertia with respect to the pivot divided by mg lowercase l. Now lowercase l has a specific meaning. You have to have watched the video about physical pendulum and understood the definition of L. So lowercase l has the meaning of the distance between the center of mass of the object that is oscillating and the pivot or the axis of rotation. That is the specific meaning that L has in that equation. So for a ring, the center of mass is in the middle of the ring, of course. The nail is on the perimeter of the ring. So that tells us that the lowercase l value should be 0.5, the same as the radius of the ring. So we got the quantity. We also going to need the moment of inertia with respect to the pivot. According to the parallel axis theorem, the moment of inertia is going to be the moment of inertia of the ring with respect to its center, right? If the axis of rotation was in the center of the ring, what would be the moment of inertia of the ring? That is what we're calling capital ICM. And then we add the mass of the ring times lowercase l squared. Again, lowercase l means distance between the center of mass and the axis of rotation. So for a ring, the moment of inertia with respect to its center is mr squared. This is a value that it's easy to remember, but if you don't remember, it should be in your formula sheet. So mr squared, mass of the ring, radius of the ring squared. And the other term, the ml squared, again, we already identified that the lowercase l is the same as the radius. So mr squared plus mr squared, which gives us 2mr squared for the moment of inertia of the ring with respect to the pivot. If we plug in the values, which we have numerical values for all these quantities, we have 2 times 1 kilogram times 0.5 squared. That will give us 0.5 kilograms meter squared. That is the moment of inertia of the ring with respect to the pivot. So we have everything that we need to put in the equation for the period. So 2 pi times the square root of moment of inertia is 0.5 divided by the mass, 1 kilogram, g 9.8, and l is the radius, 0.5 meters. Plug in the numbers and you get that the period is 2.01 seconds. So it's kind of interesting that if you have a ring, actually, if you had kept the variable m, the mass of the ring, you will have noticed that it would cancel. Numerator and denominator quantities depend on the mass, so it would have canceled. So any ring, actually, with a diameter of 1 meter, radius 0.5, when you make it oscillate, hanging from a point on the periphery, the ring oscillates with a period of about 2 seconds. So it takes this ring pretty much 1 second to go from one side to the other, and another second to come back. So, all right, so that was a physical pendulum problem.